Hello and welcome to a video on end behavior of rational functions. So in this video we're going to look at what happens as x goes towards positive infinity or as x goes towards negative infinity. And in general, the curve, the rational function, will approach a straight line. There is a possibility that it could approach a curve, but this is something that we'll look at the very end of the video, and it's not something that's going to come up in this class. All right, but so first of all, a basic definition of what is a proper rational function. And a proper rational function is just a function, a rational function, where the degree of the numerator is lower than the degree of the denominator. Okay, and when this happens, you get a rational function where as x goes towards positive or negative infinity, the value, the height, or y, or f of x, whatever you want to call it, it's all the same thing, goes towards 0. All right, so let's look at this as the first example. So the first example, which I call case 1, is where you have a proper rational function. And you're looking at an example of that right here. And this is the case where you're going to get a horizontal asymptote, but not just any horizontal asymptote, specifically the x-axis, or the line y equals 0. Okay, so this is a case where the degree of the numerator is first degree. So the degree is determined by the first term of the numerator. So the degree of the numerator is a first degree. The degree of the denominator is a second degree. That makes this a proper rational function. And so that means that the end behavior of this function, as x goes towards positive infinity or negative infinity, y is going to go towards 0. Okay, so you have a horizontal asymptote at y equals 0, meaning that as x approaches positive infinity, y will approach 0. And as x approaches negative infinity, y will also approach 0. Okay? The second case, and there's really only 3 possibilities here, and the second case is when the degree of the numerator is equal to the degree of the denominator, when they're the same degree. Again, you look at the first term. A lot of times it's the one that's drawn first, but when I say the first term, I mean the highest degree term. And in this case, just like the first case, they're in descending order. So when we look at the highest degree term, it's the first term. Okay, and when this happens, when you have the degree of the numerator equal to the degree of the denominator, then you're going to get a horizontal asymptote, but this time it's not going to be at y equals 0. It's going to be at the ratio of those first terms. So in this case, it's going to approach 3x to the 5th over 3x to the 5th, and we just have to reduce that, which is just 1. Okay, so we have a horizontal asymptote where y equals the ratio of the leading terms. In this example, the leading terms are 3x to the 5th over 3x to the 5th, so we get HA, which stands for horizontal asymptote, at y equals 3x to the 5th over itself, in this case, which is y equals 1. Now, the coefficients don't have to be the same. The coefficients could be different, and whatever the coefficients are, that's what you're going to be left over with. So if you had 3x to the 5th over 2x to the 5th, it would be 3 over 2. But in this case, it's just 3 over 3, which is 1. So as x approaches positive infinity, y approaches 1. And as x approaches negative infinity, y approaches 1. Now, again, only 3 things can happen. Either the degree of the numerator can be less than the degree of the denominator, like example case 1. The degree of the numerator can be equal to the degree of the denominator, or the other thing that can happen is the degree of the numerator can be greater than the degree of the denominator, and that's what we have in case 3. So in case 3, you're looking at a rational function where the degree of the numerator is 4 and the degree of the denominator is 3. And you can't just take the ratio of those terms. You have to go through some long division. You know, in this case, it might actually be the same as the ratio of those terms, but in general, that's not true. So let's go through the process. And the process is that when the degree of the numerator is greater than the degree of the denominator, and I said usually 1 degree higher, it can be more, but in this class, we're going to see where it's only 1 degree higher. Then you have to do division. You have to divide and ignore the remainder. So we're going to divide the polynomials and ignore the remainder. And when we do that, we're going to get an oblique asymptote. Okay? So a horizontal asymptote is just a horizontal line that a function approaches as x goes towards positive or negative infinity. An oblique asymptote is an oblique line that a function approaches as x goes towards positive or negative infinity. Let's just get those out of the way before we do the example for case 3. Okay, so case 2 and actually case 1 and case 2 both are horizontal asymptotes, and case 3 is the case where we have an oblique asymptote, and you can see the equations for case 1, that's a horizontal line, and case 2, that's a horizontal line. Case 3, we're going to get an oblique line. Okay, so we're going to get an x term in there and with a slope other than 0. Okay, so we're going to do long division here. So we're going to set this up for long division. So x to the third minus x gets divided into 5x to the fourth. And just put those zeros in there. So 0x to the third minus 2x squared plus 0x plus 1. All right, so let's go ahead and do the long division. We can't do synthetic division here because our denominator is not of the form x minus c. That's the only time we can do synthetic division. All right, so we ask ourselves, what do we multiply x to the third by to get 5x to the fourth? And that's 5x. So we put a 5x right over that 5x to the fourth. We distribute. We get 5x to the fourth minus 5x squared. I'm going to put that over here underneath the x squared term, and I'll put a 0x to the third. It won't really be used very much. As you see, when we subtract here, what do we get? We get 0 here and a 0 here. 0 minus 0 is 0. And then negative 2 minus a negative 5x squared is a 3x squared. Carry down the 0x, we don't really need to, and then the plus 1. Now we're already at the point in this particular problem where we already have a higher degree here, x to the third, so we're done. This is our remainder. The part that we found here, because it's lower degree, is the remainder. So what we're looking at here is that this is equal to 5x plus a remainder of 3x squared plus 1 over x to the third minus x. Now, we're going to end up ignoring that remainder. And the question, just briefly, is why do we ignore the remainder? And the answer is because we're looking for what happens as x gets very, very large, or as x goes towards infinity or negative infinity. So we can kind of ask ourselves, what would happen to this remainder? What would happen to this thing right here as x goes towards infinity? Let's say x were 1,000,000. If x were 1,000,000, you would be looking at 3 times 1,000,000 squared over 1,000,000 cubed. Now that may not seem like it's 0, but it's getting pretty close to 0. And one of the ways that we can look at that is we can look at this remainder for a moment and just think, what happens, how can we really analyze this remainder? And what we can do is we can say, well, if x is 1,000,000, that 1 right there, it's not doing much, right? It's really not doing anything. So this is why we look at the leading term only. So one way to think of this remainder is just as 3x squared over x cubed, which reduces to just 3 over x. And now when you ask yourself that same question, what happens when x is 1,000,000? You're looking at 3 over 1,000,000. If you look at 1,000,000,000, you're looking at 3 over 1,000,000,000. And this is going, the denominator is just going crazy and getting bigger and bigger, and the numerator is not doing anything. So this is going to go towards 0. So this whole thing just goes towards 0. Let's just put an arrow towards 0 like that. So all that's left is the other part of the quotient, and so we have y equals 5x. So this is going to be an oblique asymptote. Let's just write the word out since we haven't really abbreviated it much. Oblique asymptote at y equals 5x, meaning that as x goes towards infinity, positive infinity, that y goes towards 5x, and as x goes towards negative infinity, also y goes towards 5x. Okay, so there's our oblique asymptote, and that's the end behavior for this function. All right, so in summary, again, there's 3 different things that can happen. Either the degrees can be the same, which is case 2, and you just look at the ratio of those first two terms. The numerator can be less, which is a proper rational function, which approaches 0, or the degree of the numerator is more than the degree of the denominator, in which case you have to do long division. Now, just as a little, if you're wondering, what happens if the degree of the numerator is not only bigger than the degree of the denominator, but it's more than 1 degree higher. Well, if it's 1 degree higher, the quotient will give you a linear equation. But if it's 2 degrees higher, like in this case, 5th degree over 3rd degree, you're going to get a quadratic for your quotient. So here, when we ignore the end behavior, we ignore the remainder, we're looking at an end behavior that's going to approach a parabola. So this particular rational function, which we're not going to see in our homework, but just so you know, when the degree is more than 1 degree higher, you're going to approach something other than a line. And so here, we still call this an asymptote, but it's a parabolic asymptote. So it's actually approaching a curve rather than a line as its end behavior. Okay, I hope you found this video helpful.